If there is no medium, then sound doesn't go anywhere. The same thing was thought that since light is a wave, then the same requirement has to be there. That there must be a medium in order for light to get from the sun and the stars and the moon to us. And that medium was named ether. And at the time, it was just simply accepted that ether existed, we just didn't know what it was. The second was black body radiation. We can think of a black body radiator as a piece of coal or the embers of a fire. If I give the fire some energy, here's the energy. As it spits out that energy, it should go in a smooth release like this. And so this would be the hot, and this would be the cool. And on the way down, you should get into different colors. There should be a smooth transition through those colors. It wasn't that way. A black body radiator stair-steps itself. Yeah. And that didn't make sense. The photoelectric effect is another weird thing. Is that when light shines on an object, it excites the electrons in that object, and electrons will hop off. And that can be measured. If I shine a certain color of light, let's say on this piece of paper, then we can measure the amount of electrons that jump off of it. If we have that light on a dimmer switch and we turn up the intensity so it's really bright, we don't get any more electrons. It's all dependent on the color. If we change the color, we get a different number of electrons. So it's the color of the light and not the intensity of the light that cause these electrons to jump. Nobody knew why. So those are the last three. Don't go into physics. All we need to do is answer those and we're done. The first one was tackled by a couple of Americans, Michelson and Morley. And they had a pretty good idea of this ether stuff. They said that as the Earth is spinning and moving through space, then like water around a stone in a river, that ether had to be going around the Earth, like that. And they noticed also that as the Earth is spinning on this side of the Earth, it's spinning more into the ether, and on the other side, it's going with the ether. And so they thought that essentially there'd be more pressure here and less pressure on the opposite side, so that when they measured the speed of light, that pressure would cause the speed of light to be slower on this side and faster on this side and be measurable because the ether had to be made of something. In the 1870s or 1880s, I honestly don't know how they measured the speed of light, but they could, and they did. And when they did it, they found out the speed of light is the same no matter what direction or angle Inside, outside, upside down, it doesn't matter. The rest of the world, the scientists in the world, thought these stupid Americans couldn't do an experiment right. And they were sort of ridiculed. And this experiment was repeated around the world. And it was discovered that the speed of light stayed the same. The outcome of that was there is no ether. I can't express to you enough how surprising that was, because everyone knew that there had to be ether, because light requires a medium in order to get here, and it can't get here without a medium, therefore there has to be ether. It's like the air in this room. When there wasn't ether, it was a basic tenet of physics that went away. Confusion. The second one. Max Planck. He was a lot like you. His father was a physicist, and he told him not to go into physics. Go be a concert pianist, that's what you're good at. And so, again, like you, he defied his parents and went into physics instead. According to legend, he's not the greatest mathematician of all time. Whenever I hear his story, it reminds me of Far Side cartoon. You guys remember Far Side? Never heard of Far Side? Gosh. I guess I'm just getting old, yeah. Anyway, on this cartoon, there's this scientist, and he's writing a big, huge formula on the board. He completes one board, and he goes to another one, and keeps writing this huge, long formula, trying to explain everything, and he finally gets to a piece on the board, and he says, and then a miracle occurs, and then he continues on. So he requires a miracle to happen. Max saw what a black body radiator did, kind of had an idea of where he wanted to go. It wasn't good enough at math to get there, so he threw in an extraneous constant. It's actually Planck's constant, real small number, but it made everything come out right, and it worked. And what he said was that light comes in small packets, like particles, thus explaining the stair step. There's just a little package here, a little piece. And that's why it doesn't come out smoothly, because light isn't smooth. He called those small packets quantum. Thus, quantum physics, thus Max Planck is the father of quantum physics.
Okay, so you now know the father of quantum physics, but what is quantum
We're
physics?
getting there. Just calm down. We're getting there. So, we go back to needing the ether, and now Max Planck says light is not a wave, it's a particle, essentially, a quanta, a package. So we're explaining black body radiation. Then we get to the photoelectric effect, and that was more closely tied to 1900 or so. A young man, when he was about 18 to 20 years old, started theorizing and writing 3 papers at the same time. One of those was on the photoelectric effect. One of them was on something called Brownian motion. And if you ever go into biology and look at diatoms through a microscope, you'll find out what Brownian motion is. And his third one was something called special relativity. You probably know who this guy is, right? How old are you guys?
17.
17, 18. It's about time you guys got started.
I'm
doing
7,
something.
so I got some time.
You got a couple years.
It's not maturity age, Alex.
So when he was 25 years old, he published 3 papers.
Whoops.
Guys, this is what I was talking about. This is what I was talking about. He published 3 papers. He won his Nobel Prize for the photoelectric effect. He didn't win his Nobel Prize for special relativity. Probably because most people couldn't understand it. And I don't understand how he explained photoelectric effect without knowing what an atom was. And he couldn't have known what an atom was for the structure, the basic structure of an atom, because that basic structure of an atom didn't happen until after he wrote this paper. So it doesn't make sense that he could explain this, but he did. Here's the outcome of it explained, because I do know what an atom looks like. These are energy levels in an atom. Electrons like to exist at the home level, the level that they stay at, essentially, for the most part. But if something comes in and excites them, so you have some outside energy comes in, they can jump. And be excited. Here's the weird part. Actually, there's a lot of weird parts, but here's the weird part. If you look on this energy scale, if you gave this electron this much energy, it doesn't go up to here and kind of float. It doesn't move. Nothing happens. If you give it this much energy, it doesn't go up to here and float and stay. Nothing happens. It doesn't move. It cannot, will not, won't move until it gets this much energy. So it could jump up to here. It will skip this one if it gets this much energy, but it won't go part way. It'll either be here, here, or here, and there's more. But we'll just do 3 of them. You can think of those energy levels, actually refer back to our springs. Remember our spring lab that we did? And I had you do standing waves. You remember a standing wave, how stable it felt? And then when you tried to switch from a standing wave to the next standing wave, that it kind of nothing there, and finally it got stable again? You can think of these energy levels in an atom as standing waves, and there's nothing in between them. So let's say this amount of energy brought it up to this level. The electron does not like to be there. So as soon as possible, it will jump down. And when it jumps down, it regurgitates some energy. And it can jump down to here and give off some more energy. Eric, sit up. Sit up. Sit up. No, you're not. You're leaning down. Sit up. Third option here is to jump all the way down at once and spit off some other energy. This is the only way in the universe that light is produced. This energy that's being regurgitated here, it's being spit out, is light. And it doesn't have to be just visible light. It can be the whole electromagnetic spectrum, from radio waves to visible light to X-rays to gamma rays. Electrons being excited, jumping back down, spitting out light. This makes it a little bit more understandable because this distance from here to here, where it jumps from here to here and gives us out, is a packet. And this is a packet. Certain amount of energy. When we looked at these tubes through the spectroscopes, you saw little lines, little colored lines. Their energy levels for that element gave out that color of light because that was the distance between one energy level and the next. And so those electrons were just jumping up and jumping down, spitting that out. And you saw another line someplace else, and then that was another variation there. In these fluorescent tubes, we mix a whole bunch of different elements together so that when the electrons are jumping up and down, they spit out enough of the colors to combine together to give us white light. On the sun, the same thing is happening. Except electricity is not running into it. It's not plugged in someplace. We use different kind of energy. We use fusion energy to make these electrons jump. So again, I don't understand how Einstein explained it without knowing about energy levels, but he did. And the outcome of that was, since these are packets that refer back to Max Planck, then these electrons are doing something called making a quantum leap. And that's where that term comes from. When an electron jumps down from energy level to energy level, that's a quantum leap, or jumps up. And the reason we call it a quantum leap is that it is a certain amount of energy, no more or no less. There is no in between. There is no smooth. Questions on that? Okay, so that's what quantum mechanics is talking about. There's a lot of ramifications of it that we need to get into. The first of which is talking about or looking at what is an atom. Back in history, even back to the ancient Greeks, people wanted to know what things were made out of. And one of those Greeks thought of an experiment, thought of taking a substance, and you take that substance and you rip it in half, and then you take that half and you rip it in half again, and you take that half and rip it in half again. You keep doing that until you can't rip it in half again. And when you get down to that final thing, then that must be the brick, the basic building block of matter. And that was a long time ago. The Greek's name was Democritus, and he was actually the first one to come up with atomic theory. In fact, the reason we even talk about, refer to an atom as an atom was because of Democritus. Because Greek for indivisible is atomos. That's where we get the name. Well, that didn't quit there. People have been trying to figure out what an atom was forever. In the early 19-teens, an Englishman and a Dutchman worked on what an atom was. The theory at the time, I don't know if you, a lot of you probably had chemistry, so you know, had this before. The theory at the time was an atom was kind of like a watermelon, with the pulp being sort of a distributed positive charge, and the seeds of the watermelon being this weird little negative charge. And it was just kind of a massless, or kind of a massy sort of thing that they didn't know what it was, the structure of. But that was what the atom was thought to be. So to try to prove it, they used the gold foil experiment. Gold is very malleable, so like bread dough, it can be rolled out very, very thin. And by very, very thin, I mean an atom or two thick. They put a screen back here, a detector. And up front here, they shot an alpha particle. Again, at the time, they didn't know what an alpha particle was because they didn't know what an atom was. We know now that an alpha particle is 2 protons and 2 neutrons. What element would this be? Second element, right? It's helium. So it's a helium nucleus. So it's an alpha particle. They didn't know that, but that's what it is. So when a substance, this is a little sidelight, when a substance like uranium emits an alpha particle, an alpha emission, it gives off 2 protons, 2 neutrons, and it becomes element 90, which I think is strontium, and it's 236 and 90. This is also radioactive, and it will also degrade itself either by alpha particles or beta particles. And every time an alpha particle or a beta particle is emitted, then that atom changes to some other element. And eventually uranium gets to lead through this process, and that's where all the lead in the world has come from, by the radioactive decay of uranium, just as a FYI. So, we have this radioactive source, it's spewing out an alpha particle, and their expectation was that the alpha particle goes through this watermelon thing, gets slowed down, they could measure how much is being slowed down, they could figure out the mass density of this atom and try to figure out what the structure of atom really, really looks like. Sounds like a good idea. What happened? About 99% of the time, went straight through, didn't hit anything. Nothing. Nothing happened. Well, it didn't make sense. Gold's a pretty dense substance. You would think that you would hit these things. Nothing happened. And every once in a while, you get a deflection. Well, that was weird too. But the weirdest thing was that a few little small percent of the time, alpha particle came right back at you. Now, I can't explain to you how surprising this was, but I can explain what either Rutherford or Bohr said. They said it was like holding up a piece of tissue paper in front of a cannon and having the cannonball bounce back off of it. It was shocking. They had no concept of what this was. Obviously, their idea of an atom was not that. The outcome of this experiment is that solar system model of the atom that you all know, the Bohr model of the atom. Right? The outcome was there's a massive nucleus. That's what this happened. The alpha particle hit a gold nucleus. Gold is a very large number in the periodic table, right? So it has the most of the mass of the gold, and so this little helium nucleus ran into a gold nucleus and bounced right back off. So that's what happened. It took them a while to figure it out. And then if you remember, the electrons are on the outside of it, and they had this kind of nice little solar system model of electrons orbiting this central nucleus. We know now that it's a little bit more complex. And again, if you remember your chemistry, you remember the 1s2 and 2s2 and 2p6 and 3s2 and 3p6 and 3d10 and 4s2, and you just go and go and go. And finally you get to the F levels. I mean, it's just amazingly complex. So this would be a 1s2, a couple electrons. This would be a 2s2, a couple electrons. And then you get to the 2p's, and they're like dumbbells that go like this. And there's 3 of them with dumbbells on each, so you have an electron on each side. So there's your 6 electrons on each of these things. And then you have a 3s2 that's another circle, and then you have a 3p6. Do that same thing. And imagine now when we get to the d orbitals and you're filling those transition metals in the periodic table, we're talking about pretty complex things, structures, as far as the electrons go. Well, they didn't know that back then. They just went with their periodic table. But this also was a key. This 99% of the time not hitting anything was a key. And the outcome of that was, what is an atom really mostly made out of? What is it? Empty space. Do you know where I would put the first electron if I could blow a nucleus of this board up to this size? Where would the first electrons be? Edge of the room? Edge of the school? Sullivan? How about University High School? The first one. 1s2. Or around that. What's in between University High School and that nucleus? Absolutely nothing. 0. Empty space. If I took all the empty space out of this table, and they're pretty heavy, right? If I took all the empty space out of this table, I'm not sure you could see it. It'd be smaller than a grain of sand. It'd still have the same mass. I doubt if you could hold that grain of sand in your hand. When a giant star dies, you remember a little bit of the astronomy we talked about. The stars go through these death throes. They expand and then they collapse. When they collapse, these electrons on the outside of the atoms that are far away get collapsed into the protons. When an electron gets forced into a proton, it turns into a neutron. So you have a big ball of neutrons. It's called a neutron star. So a giant star where Mercury and Venus and Earth and maybe Mars could be orbiting inside of it, that giant of a star will collapse down to an object smaller than our moon. And essentially be a big nucleus. 1 teaspoonful of that stuff, if you could weigh it here on Earth, would weigh over 100 billion tons. That's the stuff without empty space. All matter is mostly empty space, and not just between your ears. If that's true, why does this happen? This is mostly empty space. That's mostly empty space. Why can't I shove this through this?
Is it the bonds with the atoms? Or
Close. What did we just learn about? What's on the outside of the atoms on this thing? What's on the outside of the atoms on this thing? The electrons like each other?
What's the sound of the electrons? Big mad at each other.
They hate each other. They're repulsive to each other. Is this solid? It's an illusion. Nothing is touching. It's just a repulsive force. What do you feel? An illusion. You should be able to just put your arm right through. Keep trying.
What happens when someone, like, say, assuming you're a punch into a table? Like, what happens with the electrons there? Do they just move
Same
aside
thing.
like a wedge?
When a baseball bat hits a baseball, it's just the force of those electrons. Nothing touches. I'm not really touching you. Let's see. What do we see through that? Well, we'll talk more about vision. Okay, here's what I'm going to leave off there. Here's what I want you to do. I want you to take 5 minutes and on a separate sheet of paper someplace, just write down some of what you're thinking right now. It's going to help you write your paper at the end of this. Write down some of your thoughts right now. And then I want you to read the first, I think, 3 pages of your packet.
all done.